start. Good morning, good afternoon, good evening, good night to everybody. I see that here we have, of course, somebody already announced good afternoon, but maybe we have some people who are good morning and good evening. So following the Bulgarian law, if somebody is elected for associate professor or full professor, the person has to present a public lecture on the occasion. And first of all, I want to announce that several weeks ago, our scientific council elected Veselin Filev for associate professor. So now our section of algebra has one, and logic has one more associate professor. And his talk today, this is the holographic principle, motivation, and applications. Okay, please.
Okay, so thanks for the patience. What I'm going to talk about is the holographic principle, and this is in fact a little bit of public lecture, as I mentioned. So there is not going to be that much math in it, but I'm going to talk a lot. And the holographic principle is the general framework where my research lies. And it is essentially the idea that at the fundamental level, at the level of quantum gravity, our world can be described in one less dimension as a hologram. Now, that's not the bottom line of it. I mean, if that was the only message, why even bother? As you're going to see, the holographic principle has realization within the framework of string theory as the so-called ADS-CFT dictionary, which is actually quite useful description. So let's start. So the first thing that I'm going to talk about is going to be black holes. It's not going to be some general introduction to black hole, just a very brief and perhaps sloppy definition of the basic concepts we need about black holes so that we can reach the Bekenstein bound. And once I explain what the Bekenstein bound is, we're going to arrive at the idea of the world as a hologram. This is the title of a paper by Hooft and Susskind, which is a very influential paper, by the way. And, and after that, we're going to move to the ADS-CFT correspondence, which is the realization of the holographic principle within the framework of ADS-CFT correspondence. Now, what are black holes? I mean, the main and the most simple definition that we're going to state here is that this is an area of space-time that nothing can escape. So this is a quite general definition, of course, and by this at this time we already understand that if light cannot escape, then nothing could escape, because in our understanding, at least classical understanding, well, not classical but well accepted understandings, nothing can travel faster than light. Otherwise, this would violate causality, etc. It would contradict the nature of our geometry. This is really, if you wish, since you're mathematicians mostly, stems from the signature of the space-time that we live in. And so nothing can travel faster than light. Now, the first objects that were considered with that property, that they cannot travel faster than light, were within the framework of classical gravity. And the pioneers were John Mitchell. I think John Mitchell was first, but I know that Pierre Laplace also did work on that. And they call them absolute black bodies. Now, this is ironic because black body means something else, completely something else in, or something like that. They gave a similar name to that. Black body in physics, usually it's referred to as thermodynamic black body. But it's also ironic because we're gonna find out that black holes are not only black holes, but they're also black bodies. So that's a bit ironic. But what did they consider? They just said, well, if I have a dense enough object so that light cannot escape it, which means, you know, every object has a escape velocity, right? This is the, in the probably Eastern terminology, that's called the first cosmic velocity, right? It's the velocity that you need to leave Earth. And if that velocity is above the speed of light, light cannot escape it. Even in classical gravity, that's possible. And that happens provided the object is dense enough. And in fact, you can calculate for a given mass of the object what the radius should be so that it is a black absolute body. or it's like a black hole, and that radius is very similar to the radius that you get within the framework of general theory of relativity. So this is just a curious fact. Now, in general theory of relativity, black holes are perhaps easier to understand. By example, if we look at the solution to the Einstein equations, which was due to Karl Schwarzschild's. So this is just a spherical solution. This is a solution of a stuff, of matter that has spherical symmetry. And then you have the following metric. Now here R is the radial coordinate, etc. M is proportional to the ADM energy of the geometry. So you can really think of it as the mass of the black hole. Now, what is curious about this metric is that it has a problem when R goes to 0. Like as a mathematicians, you will see that there is a problem there. And in fact, in order to know for sure that there is a problem, you have to calculate the Riemann tensor. And indeed, or the Ricci scalar tensor, etc., you can find that it's not just due to the spherical coordinates. But what about R equals to M? At R equals to M, you see this term here. Can you see my mouse, by the way?
Yes, yes.
Yes, we do.
Excellent.
By the way, just a second ago, I had a glitch, temporary interruption of the connection. So let's see what will happen at the recording. Yeah, please continue. Yeah, please continue. I am recording. Yeah.
Very good. So, as you can see here, this term in the denominator vanishes when R is equal to 2m. So that's again naively a singularity, but it's like a coordinate singularity. You can see that you can calculate the invariance of the.
Veselin, can I ask, who was John Mitchell?
He was some British monk, but was he Irish?
There's a famous Irish guy called John Mitchell, but I didn't know him as a physicist.
Was he a monk?
No, not the person I know. He was a politician.
No, that was probably a long time after. So he did it before Laplace. So maybe he was, I don't know, was he contemporary to Laplace?
Okay.
Never.
I think he was geophysicist, as I remember.
Sorry?
He was geophysicist. He was working on geophysics.
Yeah, possibly. But
yeah.
it was he was one of the pioneers, and mostly people.
Sorry to distract. I was just curious.
No. Thanks for the distraction. So, okay. So you see here that we have a coordinate singularity when R is equal to 2m. But in fact, this is just a coordinate singularity. The curvature invariance, like let's say the Ricci curve, anything that you can calculate with contractions from the Riemann tensor is fine there. But what is happening here is that the signature flips signs in some sense. You see the time has the negative signature. This is a pseudo-Euclidean signature, right? The time has negative signature, space has positive signature. What happens if you go below R equals 2m is that they flip space. And this area where this happens is in fact what we call the event horizon. Like the strict definition, what we're gonna call horizon is just the killing horizon. So if you calculate the killing vector associated to time translations, you're gonna see that it's just essentially this component here, right? And probably with the square root or whatever. And you're gonna see that it vanishes there. So a place where the killing vector vanishes is not usually, it's called the killing horizon, and that's our definition of a horizon. And now, what is also curious about is that if you go below that horizon, nothing can escape again. Not only light, nothing can escape. It's like a closed space inside. And so this is why we call it a black hole. And just to give you an idea how small or how dense rather a black hole is, if you take Earth and you try to contract Earth to turn it into a black hole, you're gonna have to shrink it down to size of 9 millimeters. So that's really, really dense objects, right? And one last thing that I mentioned about black holes, and I'm gonna speed up because I talk a lot, is that at the horizon, you also have the property of observers close to the horizon have any measurements that they do are redshifted towards the low energy sector. It's called redshift factor. It is part of general relativity. So if you're at infinity and if you see some object close to the horizon, and if that object, let's say, performs some experiment with some light, and that light is, let's say, UV light, what you're going to receive is infrared light because of the redshift effect. And in fact, all the physics that is near the horizon is going to be redshifted towards low energy limits. And that is going to be important for the derivation of ADS-CFT dictionary when we look at the low energy limit of string theory. Okay, now, okay, so we talked about black holes as these scary objects that nothing can escape from. But in fact, as I mentioned, there are also black bodies. And this was due to Hawking. I mean, Hawking considered semi-classical calculations with near the horizon of a black hole. And he showed that the black hole should emit radiation as in the same way as a black body. Now, the calculations that Hawking did are not the way I'm going to describe this physically. So what we usually what we think that the reason for the Hawking radiation is the so-called tidal forces. So what are the tidal forces? It's literally, they are the forces that causes the tidals. And they're the forces that within even Newtonian gravity are the reasons why when you have systems, they're tidally locked if you give them enough time. For example, the moon is tidally locked because that's another way of saying it, that only one side of the moon is facing Earth. And this is because of the tidal waves. So what happens is when you have two objects, the surface of one of the objects that is closer to the other one feels greater force than the opposite surface. And as a result, the object is stretched. And if the object is stretched, when the other object moves around that object, that results in some wave, like a mechanical wave that propagates inside this object. If the surface is water, it's going to be a tidal wave. But if the surface is solid, it's going to be some deformation wave. In one way or another, that would lead to dissipation and eventually lead to tidally locked systems. So these tidal forces are very, as you can see, important even when you have objects such as the moon and the Earth, which are relatively far from each other. However, when you have a very dense object such as the black hole, the tidal forces are enormous. So what happens very close to the surface of the tidal force is there is such a large gradient of the force. And here, of course, relativists wouldn't like the use of the term force, but that they can actually take a virtual pair of particle-antiparticle and turn it into a real one. And this is another notion that we have. This is the notion about the vacuum not as just being empty space, but as a fluctuating soup of virtual pairs of particle-antiparticle. So quantum mechanically, we think that the vacuum is not empty, but for a very short period of time, allowed by the Heisenberg relation, it is allowed to fluctuate, create a virtual pair of particle and antiparticle, and then they annihilate and disappear. And so the idea is that very close to the horizon, when you have this strong tidal force, it actually causes pair production. And this production of particle-antiparticles are mechanisms in which the black hole produces particles and photons being particles. It's also a mechanism in which it emits photons. So this is the reason for the Hawking radiation. And if it emits radiation and if it follows the spectrum of a black body, then it probably makes sense to talk about thermodynamics of black holes. And here, just one remark, since I'm talking to, not everyone is physicist in the audience. A black body is not black, right? The sun is, to a very good approximation, black body. If you look at the spectrum of the sun, it is very close to a thermodynamic black body. So that's why it's ironic that the black holes were first called black bodies, then they were, scary black objects, and now they're again black bodies in the sense that they radiate and they're not black. So good. So now we can talk about temperature of a black hole, and this is what Hawking did. And if we have thermodynamics, we can talk about the first law of thermodynamics for black holes. Now, usual thermodynamics relates on the right-hand side the change of the internal energy to the change of the entropy of the system and some work done on the system. Now, the energy here is just the ADM mass of the background. The ADM mass is, you can look it up, it's some definition in which you can define a mass for a gravitational background. And what is here, A is the surface of the horizon. This T is the temperature, it's the Hawking temperature that you can calculate. And this is just the, let's say, the angular momentum and the charge of the black hole. So this here is like the analog of work, if you remember the usual from school, usual thermodynamics. And it's this term that it's important, that is multiplying the temperature, because we should interpret it as entropy. And in fact, this is what describes the entropy of the black hole. So this is how you can calculate the entropy of the black hole. Now, the second law of thermodynamics states that the entropy of a closed system should not decrease. Now, this immediately translates to the fact that if this is correct, when you deform with any allowed dynamics within the framework of GR, the event horizon, its area should not decrease. Of course, here I have to say that this is only if we ignore small Hawking radiation and if we consider it small, because if Hawking radiation is very large, of course you cannot ignore the part, the black hole is not a closed system. You have to consider the whole system universe plus the black hole. And then you're going to see that it's thermodynamically unstable, most of the black holes, etc., etc. But if you consider either a very short period of time or like a regime in which the Hawking radiation is small, this is a, when we're in equilibrium, this is a very good approximation. And so as I said, this allows us to interpret this term here as an entropy. And this is called the Bekenstein-Hawking entropy. So this is how we arrive at the conclusion that black holes should have entropies. Everything should have entropy. But what is really puzzling for people here is that the entropy is proportional not to the volume of the black hole, but to the area of the black hole. And the entropy is extensive quantity. Like if we think classically, it should be proportional to the volume. Just like if you think of, for example, the mass of an object, if you double the size of the object, the mass doubles. Okay, if you think about the magnetization, these are, or the volume, these are all extensive quantities. They are proportional to the size of the system. Why is the entropy of the black hole proportional to the size of the boundary of the system and not the system? This is what is very strange. And it's in fact what motivated the holographic principle, because it says that perhaps you could describe at fundamental level, when you talk about quantum gravity, you could describe the interactions within the boundary. So, and a hologram, I should mention, as we know, is an object that maps three-dimensional object into a two-dimensional film. And that's why the idea of holograms. But I'm going ahead. So, okay, so we have this definition of entropy. And Bekenstein went further and he said, well, okay, this is the entropy of a black hole, but I have all reasons to believe that entropy is a maximal, and the black hole is a maximum entropy object. So if I want to fit the most entropy into a given region of space-time, I have to fit it into a black hole. And if you think of entropy as being a measure of disorder, this makes sense because everything that goes inside the black hole is scrambled. And so it would make sense that it's a maximum entropy object. But we don't even have to rely on that. We're gonna have a very hand-waving, not even physicists' proof of the Bekenstein bound. So another thing that I want to mention about entropy, and I'm sure a lot of you, or probably all of you know that, is that entropy, people talk about entropy in information theory also. Like I here is the Shannon entropy. So what Shannon defines entropy as the average information that the system has. So you consider the information that is associated to a given state of the system, you average over all states, this is your average information. And it's related to the so-called von Neumann entropy, which is in fact the thermodynamic entropy that we derive from statistical mechanics, just by a scale. And the scale here, the log of 2 appears because the definition of one bit of information for Shannon is the information that you have of a Toyn-Cousins experiment, whether you have heads or tails. This is the single bit of information you can have, a binary yes or no, and from there it comes the log of 2. But other than that, we have informational interpretation of entropy. And so if we have Bekenstein bound, if we have a bound for the maximum entropy that we can fit within certain region, it means there is a bound for the maximum information that we can fit with certain region. And there is a curious calculation here, which is, you can find in Wikipedia, by the way, is you can calculate the Bekenstein bound for the human skull. Why I'm saying the human skull? Because the brain is a complicated folded object. It has very close to Hausdorff dimension, right? It has fractal dimension, so the area will be very large. But you can fit the brain obviously inside the skull, and I can calculate the area of the skull. And this is the maximum information that you can fit within your skull, according to Bekenstein. So that is, at least we can relax, because we know that's a huge amount of information. We can never reach our Bekenstein bound, or as I joke with my students, they cannot use it as a complaint that they didn't study for the exam, because they cannot say, well, I studied too much and I just saturated my Bekenstein bound, so no information here. So that's not gonna happen, at least not due to Bekenstein. Now, so let's motivate the Bekenstein bound. Well, consider that it's wrong. That's what mathematicians often do. So we assume that the opposite is true. So you take a region in space-time, and the area of that region is A. And now you say, well, let me calculate the Bekenstein, with the Bekenstein formula, the maximum entropy that I can have inside this region, and it is going to be the number. And now you say, well, I now assume that the stuff that is inside has more entropy than the Bekenstein bound. We're gonna show that it contradicts something. So now what we do is we throw in some extra matter. Throwing extra matter, I bring more information into the system. I can only increase the entropy. So I increase even further the entropy. But adding more matter, I could eventually keep doing that until I reach the critical density that is sufficient for the matter to start collapsing into a black hole. And eventually it's gonna collapse into a black hole inside. But since the black hole is inside the original region, and all the matter is inside the black hole now, I can calculate the total entropy now by calculating the area of this black hole that is inside. And since it's inside, it's going to have smaller area and hence smaller entropy. So it seems that I started with some entropy larger than this quantity. I added more entropy, the system evolved, and then I ended up with less entropy. But that means the entropy decreased, and since it's a closed system, this violates the second law of thermodynamics. So if you want to keep the second law of thermodynamics, you need the Bekenstein bound. And you can here realize why this works for black hole. We never used any Schwarzschild radius, nothing. Well, because we, yeah, let's not get there. But it is because it's a maximal entropy object. So now, this was the realization that it's not only valid for black holes, because you could just say, well, black holes are weird objects. Maybe they're not even real. Maybe they're just, you know, mathematical abstraction. You know, they're not physical. But with these considerations, you could probably still say some of these things. But it makes more plausible that there is such a bound. And by the way, just by saying these things doesn't make them true, right? And now, so this led to the conclusion by Hooft and Susskind that they can actually describe quantum gravity as a hologram. And this is the name of a paper. It's a seminal paper. It's not technical, like just the first part of the paper. It's not technical, the rest is a bit technical. And it describes this idea that the world can be viewed as a hologram. So just like as mathematicians, you know, I could imagine that I take my space-time and deform it in such a way that I send the boundary at infinity. And I can think of this holographic screen with whatever map you prefer as your boundary. And I can say, well, this is my holographic screen. This is where I measure my entropy. This is where I know about the degrees of freedom of what's living inside. So I should be able to map all the physics that is going on in the bulk of the geometry to this holographic screen. And they consider a toy example here, just to see that this structure is very natural for general relativity. And they say, well, really the world is very complex things. So let's consider something called partons. So this, we imagine that there are these small particles, and we call them partons, and we're going to map them to the holographic screen using light rays. So we let the light evolve according to the, it moves around now geodesics, as you know. So we let the light evolve, and we let it pierce the holographic screen at some point. And then we say, well, then that's our map of the parton to the holographic screen. Now, let's see if that's a consistent map. Let's try to map the area of a black hole. And naively, you would expect that the left half of the black hole would never reach it to the holographic screen, but it does, because light is bent, because the geodesics are bent, not geodesics. In fact, you can show that all the area of the event horizon is exactly mapped into a disk in this holographic screen. And not only that, but the holographic screen being a boundary, its area should also be a measure of entropy. And so if I have that, I shouldn't lose information with this map. And if I don't lose information, I shouldn't decrease the area of this image, let's call it. And there is a theorem like that in GR, which is called the Focusing Theorem. And it actually states that if you do exactly that, the area of the image of the black hole will be greater or equal to the area of the black hole. So it is very natural for this interpretation of the holographic screen that the area does not decrease. Now, we could try to break this description, and we say, well, what if I hide something behind the black hole? I'm going to put something behind the black hole, and I'm going to hide it. So I'm going to put another black hole behind that black hole. And what happens is, again, that's because of the way GR works, you cannot really do that. You cannot actually hide one black hole behind another black hole. No matter how close to it, well, unless they merge, of course, you bring it to it, or it's strictly behind it, the light always goes around and actually produces this image, like this ring image, which again has the area that is equal to the area of the horizon or larger. And so it seems that you can indeed map everything to that holographic screen. And in fact, if you want to see, you could say, well, maybe that was a very particular solution. Maybe I could, perturb it a little bit, it would change. In fact, you could trace numerically. You could say, well, what if I now have two black holes? These are their images, and I try and hide the smaller one behind the bigger one. As you approach as the big one is about to eclipse the small one, this image here starts forming, and it has exactly the same area as this one. Then eventually you see the ring, and then eventually when it goes on the other side, you see this. And at any point, the areas of these images remains constant, or rather remains above the limit of the radius of the horizon. I'm not sure. No, I think it remains constant. Yes. It behaves as a fluid that cannot contract, right? It's non-contractible fluid. So it really behaves that way. And okay, so these are just the hand waving and first part of the paper that I said are accessible. After that, they go and elaborate on this idea with some more machinery. But there is no, this principle is not complete, right? There isn't an equation that would allow you to map yourself into the holographic screen of the universe. And no one is actually looking for it. We're not asking the astronomers to find this holographic screen. It may not, it is just a theoretical concept. And also notice that when I did this mapping, I could have done infinitely many analogous maps. I could have taken the light rays not to go this way, but slightly tilted, that would produce different pictures. So there are more than one pictures, right? Not a single one. And some people try to say that corresponds to coherence in quantum mechanics, etc. But it is, let's leave it like that. So let's leave it like a motivation that it is very suggestive that the way that quantum gravity works is that there is a Bekenstein bound, and that suggests that we could describe the whole world as a hologram at some holographic screen at infinity. Now, what happens is that within string theory, let me just see what time is it. Yeah. What happens is that within string theory, we could actually realize the holographic principle. And this happens with the so-called ADS-CFT correspondence. Now why in string theory? So string theory is our best candidate for quantum theory of gravity. Not only that, but gravity is actually a low energy limit of string theory. In fact, that's why it's our best candidate. If we could have a quantum theory of string theory at low energy, we automatically get quantum theory of gravity. And I should say that it is true for the spectrum of closed strings. Now, on the other hand, we can describe gauge theories. Gauge theories are the theories like quantum electrodynamics, quantum chromodynamics, the theory of electroweak interactions. It's essentially our standard model. Our standard model is a gauge theory. So we have these two alternative descriptions. We have this description of all the interactions that take place, all the experiments that we do in CERN, and they all has to do with gauge theories. But what theorists are still lacking is a complete theory of everything that unites gravity and does the same thing for gravity, that quantized gravity. So string theory is such a candidate. The problem of string theory is too related to reality, but that's not a problem for us, for what our goal is, because we're going to use string theory exactly as a framework, like a powerful framework that allows you to generate toy universes and do tests in them. And okay, and one last thing to close the cycle is that open string theory and closed string theory are actually the same theory, because when you consider interacting open string theories, two strings can join and it creates closed strings. So you can see it's very, very easy. Now, so let me say a few more words about string theory. Again, very high level. If we think of our standard model as a theory of particles, and if we think of the particles as some points, zero-dimensional objects which have some properties like spin, charge, etc., and we think that this zero-dimensional object is approximation of something that has, like a small sphere, etc. So the analog of that is to promote, in string theory, is to promote this fundamental object that is zero-dimensional to one-dimensional string. And this string can vibrate, and all the vibration of the string, it's literally a string, by the way. The standing waves of the string, in some sense, when you quantize them, it would have the spectrum of the whole piece. It would have the spectrum of the standard model. And it's not that it cannot have it, it's just that it can have so much more. Like the problem with string theory is that it can describe so much more than what you need. And now, to visualize this, consider an interaction of two particles. The two particles are joining, and let's say a third one is produced, which is, usually violates the conservation of momentum, but for our purposes, it's good enough. Or never mind, ignore that last comment. Now, if we now consider that instead of these particles moving in the center, we have closed strings propagating, we're going to have these tubes here connecting. And this picture is in, in Minkowski space. So now you can slice it with constant time slice. And depending on the boosts on essentially your coordinate system, you're going to slice it at different angles, and you're going to produce different pictures for the interaction of the strings. You could either, the point where the strings split will depend on how you slice it. So this is already suggestive that string theory is non-local. So the interaction in string theory depends on the observer. So this is, there are non-local theories. They're difficult to handle. String theory is one of them. Now, and as I said, the normal modes of the strings describe different particles. So perturbative string theory, it's the analog of perturbative field theory. In perturbative field theory, we consider something called loop expansion. This is, you can think of it as Taylor expansion. Well, you can think of, you can consider you have path integral, which in the mathematical literature, I think it's continuous integral. And if you expand in that integral the action of the theory with respect to some small parameter, let's say the coupling of the theory, which is the constant of interaction in another language, you're gonna obtain different orders of perturbation theory, and they have the meaning of different loops of virtual particles. So you allow different loops of virtual particles. It has to do with this initial picture that I told you about, that we think about the vacuum as fluctuating particle, antiparticle. So the analog of this loop expansion, we say loop because we imagine that one virtual particle is created and it's closed and it describes a loop. And in string theory would be expansion in different genus of the surface, because a string theory being one-dimensional object, when you consider its dynamics, its evolution in time, would describe a two-dimensional world sheet. It's called world sheet, and it can have different topologies. And now you could say, well, can I, in perturbative string theory, expand in the string theory coupling, but I break down my expansion further into expansion of different genuses. And in fact, you don't even have to do that. But if you do your perturbative expansion in small gs, it organizes in expansions in different genus. You can check that. It follows from the action of the string. It has a term multiplying the string coupling is multiplying a term that gives you the Euler characteristics. It's integral of the scalar curvature properly, and so so you have this property of string theory that you can take the partition function, which is a function that describes the theory, and you can expand it in Euler characteristics in topologies. Now, any questions? I'm talking fast because time is going. Good.
Do you have questions or comments?
I have one simple question.
Yes.
You say that the standard model is a gauge theory. I think a standard model standing in your ADS-CFT slide, it's standing for the CFT part, right? If you use field theory to describe the particles, and that's all.
Yeah, go ahead.
But if you think about the bulk, the gravity part, so writing the gravity in 4 dimensions, at least as a gauge theory, it's not very clear. We have some things in 2 dimensions or 3 dimensions, but for 4 dimensions, it's not very clear, as I know. So
yes.
Do you think ADS-CFT, do you think ADS-CFT can be interpreted simply?
Let me just mention, we don't rewrite gravity as gauge theory. We have a duality between gauge theory and gravity, and you do gravity just like as you do gravity, you do gauge theory as you have gauge theory, and this duality is some map between them. And the duality that we're going to realize is going to be in 10 dimensions in a rather but you don't rewrite gravity as gauge theory. It doesn't come from there.
Oh, okay. Yes.
And now, and in fact, it's going to be become. But thank you for that. It's a good observation.
Thank you very much.
Thank you. Somebody asked about Leibniz, Laplace, and this. I found in internet this in the chat some information about the black holes. You can see this in the chat. This is. I simply copied and paste from internet.
Yes. He was Irish. Okay, sorry, that's dangerous comment. Sorry. Yeah, we are someone plus. Yeah, good. Yes, thanks. And now, what Hooft? We're going back to Hooft. So Hooft is, by the way, I think he's 74 years old. But what I'm going to show, he did, I think, 40 years ago. Danger, do you know when he did it? I think it was 40 years ago.
You're going to Give me a hint as to what the subject is.
The large chain 't Hooft limit.
Oh, it was, yeah, it's 75 maybe.
So 45 years ago. So 46 years ago, he did that. That's why I'm always surprised when I know that he's 74. But anyway, so Hooft did the following. He said, well, let me consider Young-Mills theories. And Young-Mills theories are, again, gauge theories. Actually, they are gauge theories. But the Feynman diagram that I drew there was one-dimensional. But in gauge theories, our fields are actually transforming in the adjoint representation of the gauge group. And we consider the adjoint representation as a cross, as a product of the fundamental and anti-fundamental. And because of that, they're described by matrices, which have two indices. And because of that, you actually have double lines. So let's say if you describe the evolution of fundamental objects, such like fundamental means fundamental fields transforming in the fundamental representation. And it so happens that the fundamental particles that we are built out of are also transforming in the fundamental representation. But now, so they're one-dimensional. But since they become matrices now, you actually describe these interactions with two-dimensional, so-called fat Feynman diagrams. And being fat, they're naturally mapped into a surface. You can ask the question, well, if I have this Feynman diagram, can I write it on a surface? And the topology of the surface that you can write it will have some other characteristics, and you can have, there is a definition about graphs that you can actually come up with an Euler characteristic that will exactly match that one. And in fact, in this large chain expansion, when he considers the large chain expansion of Young-Mills theories, where n is the size of the gauge group, so he considers the theory and then he extracts the size of the gauge group, he does this expansion, and he sees that it organizes again into topologies of the fat Feynman graphs. So, for example, this graph, I can visualize it as I wish in 3 dimensions, but in 2 dimensions, I cannot fit it unless I have a topology with a handle. Right? And so you have this, again, all the characteristics of this Feynman, of this fat Feynman graphs. And when you expand the partition function in large chain of Young-Mills theory, it organizes in the same way as that one here, you see. And then he said, that's in the 1970s. He said, well, then I should have duality between string theory and gauge theories working in that regime. Of course, at that time, no word about holography, but it so happened that 24 years later, it was realized within the framework of string theory, exactly satisfying this regime, and on top of that, satisfying holography. And this is the idea of safety correspondence. But from the early days of both string theory and gauge theory, so it's probably little known fact, but string theory actually predates gauge theories. So from the early days of, and it was again proposed by Susskind, by the way, the same guy with the holographic principle. He proposed string theory as description of hadrons, some jet trajectories. He didn't have this, megalomaniac idea of proposing theory of everything. That came much later, but it was started with him and Veneziano and some other people. Okay, now, good. So this is a lot of motivation, and in the last 10 minutes, I'm going to try to. It's 1 hour, right?
Okay, you can speak.
Yeah, sure. Okay, so now, okay, I've been talking about string theory, but string theory doesn't have just strings. In fact, string theory has something called d-branes, which are as fundamental as the strings. And let's see what are these strings. And now, the strings being open, like literally, classically, imagine a string in space, n-dimensional space. The end of these strings are allowed, there are rarely points, and these points can roam the space. What if I limit them? If I limit them to move around certain surface, just like here. Well, that surface is called d-brane. Like most people say that d-brane comes from Dirichlet branes, from Dirichlet boundary conditions. And it's probably true. Okay, now this, then let's consider a stack of such d-branes. Just to mention that you can show from the theory just that because, well, I'm actually going to motivate it. Now, the stack of D branes, the ends of the open strings, they are actually charged as fundamental fields. And if you give orientation to the string, one becomes fundamental, the other anti-fundamental. And in fact, the open string ending on the D brane is naturally described by a gauge, by a gauge field in the adjoint group. In fact, it gives rise to Yang-Mills theory. So if you look at low energy limit, you can, and you write down the action for these objects in string theory that you can derive consistently, by the way, also. You obtain that super Yang-Mills theory is the low energy limit of these objects. Now, on the other hand, these two strings, for example, can join and they can emit closed string. But closed string has gravity in the spectrum. So therefore, D branes are source of gravity. You don't need this argument, of course, just because they have tensions, they will be already tension, they will already be sources of gravity. But there were, at the time when these D branes objects were developed by Joseph Pulczynski, who recently died, very, very smart Irish, I would say, well, Americans with Irish roots physicist. There were already these extended objects in supergravity called p-brane solutions. And people realized that these p-brane solutions, when they study their properties, are actually D-branes. So there are very nice papers in which you can map the properties of these objects. And they're the same objects. And since gravity is low energy limit of string theory, these are two different low energy descriptions of the same object being D-brane. And that's how the ADS-CFT correspondence was arrived at. One looked at D3 brane. D3 stands for the number of spatial direction, which if our world was a brane, it would be a D3 brane. And that's what Maldacena did, essentially. So he looked at these two alternative descriptions of these objects, one in gravity, another in Yang-Mills theory, and he provided evidence that there is duality between them. Well, motivation, I should say. There is no strict mathematical proof of the ADS-CFT correspondence as yet. Now, so looking at this alternative description, he arrived at this conclusion. The type 2B string theory on ADS5 x S5 spacetime is dual to n equal 4 super Yang-Mills with rank n. This calligraphic n here refers to the number of supersymmetries. So the supersymmetries is essentially the number of, never mind. It's just some property of the theory. And this n is the rank of the gauge group. And ADS5 x S5, ADS5 really is like a hyperbolic sphere. So this is really a very highly symmetric space. Like ADS5, you can show that if you look at the solution with maximum symmetry, ADS5 is one of them. So it's a very highly symmetric solution. And then the radius of the string of the both ADS and the sphere can be related to the string quantities, and in fact can be related to something called the lambda the 't Hooft coupling. And this is exactly this regime that is suggested because the radius depends on n here. It's exactly the regime suggested by 't Hooft. And also, if we want the gravity description to be valid, we want the curvature to be small. And the curvature to be small means the radius of the curvature to be large. The radius curvature to be large with respect to what? With respect to the length of the string. But the length of the string is related to the coupling of the string and is ultimately related to the so-called 't Hooft coupling. And so now we have this relation that essentially states that if we want gravity to be in a good description of reality, which means we want the radius to be of the curvature to be much larger than the string length, then we need the dual theory to be strongly coupled. And this is why this is a weak strong duality. There are such dualities, other dualities like that. And the weak strong duality allows us to map the tractable regime of one of the theories into the untractable regime of the other theories and vice versa. So that's why it's useful actually. It allows us to access the non-perturbative regime of these gauge theories that we have as duals. Now here, of course, the caveat is that this is n equal 4 super Young-Mills, and when I was asked the question, I thought that that's where it was going. Indeed, n equal 4 super Young-Mills is conformal field theory. So conformal field theories, they are conformal in the sense they have conformal symmetry, they are scale invariant. We're clearly not scale invariant, right? So that cannot be a consistent description of reality. So of course, you can tweak the correspondence, you can break conformal symmetry, etc. You could modify it, but in its original formulation, it's very abstract, as you can see. It's this abstract n equal 4 super Young-Mills theory, which is conformal. It's mapped to this abstract space, ADS5 cross S5 space. And here it's a representation of the ADS5 cross S5 space, and you can compactify it and obtain some boundary. This is really schematic here, but you can make it more precise if you wish. And then this fifth dimension, the radial dimension, has interpretation as energy scale. So in all these gauge theories, in the theories of the interactions of particles, etc., it makes sense to specify the energy at which the interaction takes place. It's different at different energy scales. And that's how intuitively you can think where the fifth dimension arises for. So you consider a 4-dimensional gauge theory, you have some interaction, but now I have to specify the energy scale at which it takes place. And so this parameter is actually mapped to the radial direction of the ADS. And going further into the bulk of the geometry corresponds to renormalization group flow. So it's a very beautiful picture. And it's in fact quantitative. So that there are ways to relate the partition functions of the two theories, and we could use them to actually have the so-called ADS safety dictionary and extract information that we do by calculating in gravity about the properties of gauge theories. So this can be used to in high energy physics, in heavy ion collisions, and in chiral symmetry breaking, for confinement, in condensed matter theory, for superconductivity, Hall effect, etc. These are all strongly interacting systems that are difficult to describe. Confinement is difficult to describe, chiral symmetry is difficult to describe, and the heavy ion collision I'm going to talk more about. So this is really my last topic.
Okay.
So before, sorry, yeah.
No, you continue.
So before that, I want to remind you what is viscosity. So this is an actual experimental result that this is the closest, to my knowledge, the string theory came to making an experimental prediction. So if you have, let me remind you what is a shear viscosity. So there is something called bulk viscosity. This is essentially the resistance of due to contraction, but the shear viscosity is when you have a laminar flow, and if you have a fluid flowing in this direction, the layer that is closer to the surface will remain stationary. It will be stuck to the surface, and then each layer will have friction next to another layer, and this friction is proportional both to the area of the layers and the gradient of the velocity, and the tension is the coefficient of proportionality of the tension is in fact this shear viscosity. So if the shear viscosity is low, there is not so much tension, and the gradient would be different. And yeah, now this quantity you can calculate it, and you can also calculate the density of the entropy that we talked about. And if you take their ratio, you see that it has the following dimensions, and you can actually calculate this ratio in kinetic theory of particles, and you'll see that it's proportional to the mean free path of the particles. So this is here again just to, as a curious fact, the ideal gas, which has infinitely long mean free path, because in the ideal gas we make the approximation that the particles are not interacting, has infinite ratio, infinite viscosity versus entropy ratio. So it's in fact not an ideal fluid, right? good. So it's the opposite. It's a perfectly unideal fluid, if you want, the ideal gas. But the bottom line is this is a very large quantity. Usually it's expected to be very large quantity. However, recently, and it's not so recent anymore, but it was like 10, 15 years ago, people started obtaining a new state of matter in RIC and LHC experiments by colliding heavy ions. So they take an ion, let's say lead ions, they look like pancakes, they collide them with very large, enormous impact. And what's created for a very brief period of time is a new state of matter called quark gluon plasma. So as you know, we're made out of atoms, and when the atoms are heated, the next state of matter, we can think of it as the usual plasma, the one that is in the sun. Now, so the quark gluon plasma is when you do the analog of that, but for the nucleus of the atom, and that's very difficult to do. It was theorized at the end of the 90s, and here I should say that quantum chromodynamics, which describes the strong interaction, which essentially tell you how it's responsible for the physics of the nucleus. Well, not only, but yeah. It is asymptotically free. There is a Nobel Prize given for that it was shown that it's asymptotically free, which means that it becomes weakly interacting at high energies. And because of that, there was a big industry in the 90s. People were calculating quark gluon plasma, assuming that since you heated the system to such large energies that you melted the nucleus, the theory should be at high energies, therefore weakly coupled, and there are a lot of properties of the quark gluon plasma before it was experimentally obtained that were assuming that it's weakly interacting because it's at high energies. But they obtained this quark gluon plasma in these experiments, and it turns out that it doesn't behave but at all as predicted. In fact, it is very strongly interacting. And the reason for that is deconfinement, because when you deconfine the quarks, they actually, you obtain many degrees of freedom, and the energy per degree of freedom actually drops much more than actually you pump the energy. And so in fact, it's not strongly interacting. And it was only accessible with lattice models or ADS-CFT. And so another thing that they did was they expected that they're going to see a number of the order of 1. What they were obtaining actually for this shear viscosity versus entropy density ratio was that it was a very, very small number. And there is no theoretical description why you see such small number. In ADS-CFT, you can actually consider a black hole. In this black hole is not a black hole, it's a black membrane because it has some non-compact directions. So the horizon is not a compact sphere, the horizon has non-compact directions. And in other sense, it has thermodynamic modes, hydrodynamic modes. So you can do transport and you can actually calculate the viscosity of the horizon. You can even calculate and you can calculate this ratio about in some sense, the viscosity of the horizon. Of course, you can calculate this ratio from the horizon. And this ratio is this very small number, which is a constant, and is this universal bound for the entropy versus viscosity versus entropy density ratio that was proposed in this paper. And it's not really a prediction of string theory, but it was, it's small enough number to not contradict the observations that were made by these experimentalists. Now, purely theoretically, people actually violated this bound by producing backgrounds that violate this bound. So it's not clear how universal it is, but it is still a nice way of obtaining something related to reality out of this something quantitative. Otherwise, qualitatively, you can describe a lot, but you could hope to describe something quantitatively here. Okay, and this is my almost last slide. It's just a picture of two heavy ions colliding. They're pancakes because of the Lorentz contraction, because they move with very large velocities. There is Lorentz contractions, and instead of spheres, they look like pancakes. They collide, then there are some processes here, and in this hydrodynamic evolution, it's the region where you have the quark gluon plasma. And one curious property about this quark gluon plasma is that when it starts expanding, it thermalizes, and then it starts expanding faster than it would thermalize. And it's called hadron freeze-up. And this is exactly analogous to the to inflation in cosmological scenarios. So our modern understanding of the universe is, well, our present understanding of the universe is that it underwent a very rapid expansion called inflation, which is the only way that we can, at least so far, explain why we see anisotropies of the microwave background radiation. So we look at different points of the sky, and these points are not the anisotropies. We could describe the opposite, why it's thermalized. So we look at these different points, and we see that these different points are thermalized, even though they're not causally related. So how can you thermalize with something that you're not causally related with? If you go somewhere in Papua New Guinea and you find a small village and they speak exactly with your local accent, let's say in some neighborhood in Sofia, how would that be? I mean, they are not causally related. So that's what we see with the sky. And we assume that that's because, like, very long time ago, the universe was much smaller. They were causally related. They thermalized, the radiation thermalized, and then it expanded very fast and freeze out. So the same effect, exactly the same effect you see in these experiments. And just, this is really the last, you can, in fact, try to mimic some of this by colliding numerically, by considering merging ADS black holes. So this is the picture that you get numerically for merging two ADS black holes, and you kind of imagine that this looks like this. I didn't follow too much this line of work. I don't know to what extent it was successful quantitatively, but it is, there are such attempts. Okay. And in this, some other applications, these are other applications, I'm going to skip them. It's just that qualitatively different results from perturbative regime of QCD can be explained here, right? And then it has happened that when you, I know of such examples, by the way, that when you discover something through ADS safety, it actually goes and the people who do this theory consider it and then develop their own theory also. Okay, that's it. Thank you.
Okay. We thank the speaker, not only his to us. Do you have any questions or comments? Okay, Davut.
One comment. After the important was, mine is not important.
Well, yours is the most important, seems.
If there are no other comments or questions, then I will say something.
If there are no other questions, let's thank the speaker once again. And I am make an announcement for the next seminar. This is the next Friday in the same time. This is 4 p.m. in Sofia, 1 p.m. in London. Alexander Zubkov will speak on crude dimension of Newtonian superrings. Then in 2 weeks, we have Good Friday in the Orthodox Church. So there will be no meeting, but there will be a meeting one day before the Good Friday. Petr Danchev, he became an associate professor in algebra. So he also will have his lecture, similar to this lecture now. And then the next meeting, this is the 7th of May. After this, we have some invitations, but not confirmed. If you go to the homepage of our seminar, you can see the titles. And the announcement is a mixture between Bulgarian and English, but several days before the talk, there will be also an announcement in English at the homepage of the Institute.
Veso,
Yeah.
4 p.m. in Bulgaria is 2 p.m. in England, not 1 p.m.
Okay, this is the universal time.
Ah, okay. But the real time there is 2 p.m.
So they
Okay.
have daylight savings time too. Yes.
Yes, they have. they have.
I should say the universal time UTC.
Yes, yes. If you say GMT or UTC, it is 1. But the time that they live in England and Ireland is 2 p.m.
In the message, usually I write that the talk is +3 UTC in order to be sure. Some other comments or questions?
One more congratulations to Veso. It was a very nice talk, even for people that understand something from the subject.
Yes, it was. I enjoyed it very much, Veselin. That was very, very nice.
Thank you, thank you.
And I was curious to know, just out of curiosity, can you argue for the black hole spherical symmetry of the horizon from those tidal arguments? Has somebody gone through that argument?
Well,
I enjoyed that part of the talk very much as well.
no, I understand, but
familiar to me.
I think what I'm actually curious is, I'm going to slightly shift your question. Can you rederive Hawking's radiation using tidal arguments?
Yes. Okay.
I'm not sure actually. I think I can. Qualitatively, you can. I know qualitatively, but quantitatively, do you think you can? Maybe you can. I don't know. But it's worth. Otherwise, for the spherical symmetry, what do you? Can you elaborate? What do you mean?
I'm thinking of Birkhoff's theorem. For instance, just a physical argument for why spherical symmetry is so universal in black hole physics.
Ah, I see. Yeah. Well, there is the black no hair theorem. It goes somewhat close to that. And you know, if you have the universal is really, you know, the care because you have rotation. But eventually that's going to die out because of, you know, radiation of the gravitational waves. So yeah, I think the no hair theorem maybe because, but I'm not sure really. I'm not sure. Yeah.
No, but real black holes are not spherical, but they have these quasi-periodic modes of oscillation that die out fast, whatever. So spherical symmetry is just for convenience. Theoretically, it's most often.
No, but what Andrew says is that usually, ignoring the...
Ignoring transients, those ones would die out with time.
Yeah.
But you should be able to. Veselin's argument suggests that those would be associated with the tidal forces, and they would wash out with time.
So you want to consider it purely mechanically why this?
Yes, yeah. I don't want to do any mathematics. I just want to.
No, I understand. So any deformation, okay, maybe. Yeah, I don't know. It's if there is really sitting something there is just, you know, space-time there. But who knows? Maybe there is like maybe you could apply that to a collapsing object. Maybe I don't know. Yes. Okay.
Also, I have a technical question. Usually, recently we started to record the talks and then post them in YouTube. Do you agree that your talk will be also there?
No, I'm kidding. Of course, I agree.
Okay. So you can tell the other people that if somebody missed the talk and wants to see it will be in YouTube, simply go to the homepage of the seminar, and there is video there, so you can do this.
Thank you.
Also, you can give Elitza the presentation to post it, if you want.
Yeah, sure, yes.
Okay, thank you.
Yes. Okay, well, thank you for listening. I know it was a long talk.
Vesco, the speaker, Veselin Filev.
Yes.
So maybe I shall express my comment because it's quite interesting for me. So your talk was very interesting to me. I could not understand all the technicalities, but here and there I grasped it because you explained everything in a very nice way, even here and there intuitively. So perhaps we can go to the picture back with the two poles where you were talking about the lack of the causal link. Just 2-3 pages backward from the tank.
You mean that one, right?
Yes, here. So you said that between the two, those objects, there is no causal relation.
Yes, yes. I should thank you. I should have specified with respect to the speed of sound. So
Okay.
it's not with respect to the speed of light, right?
Okay.
You're just thinking of it as hydrodynamic object, and in hydrodynamics, the analog of speed of light is speed of sound.
Okay.
In some sense, okay. Don't quote me on that. But the thing is, it's a medium. It's like a medium, and just like you can think of space-time as medium, that's another medium. And it's in fact there are analogies. Like as you know, this shock wave. The shock wave happens when you move faster than speed of light. It's like if anything travels slower than speed of light. In some sense, before the wave arrives, the medium knows that the wave is coming, right? But if it travels faster than speed of light, it doesn't know it's coming. So speed of light is really like your analog of transporting information in this medium. And so, and because we're talking about thermodynamic equilibrium, it is part of the hydrodynamic description. So whether the different objects, different parts of this fluid are thermalized, they're in thermal equilibrium. For that, they need to, be able to feel each other's temperature, if you wish. And if they expand too fast, they cannot do that. It's a bit more complicated than that, but it's the speed of sound that you expand faster than the speed of sound. Just like in the other picture, it's a very good question, by the way. In the universe, we know that it expands faster than the speed of light, right? That's what determines the causal region. Here, the analog of that would be the speed of sound. It determines its causal region too.
Okay. Okay. Thank you. It's a very nice explanation.
Thank you.
The whole talk was very pleasant.
Thank you. I'm glad to.
Okay. Some other questions or comments? Okay. Yes, thank the speaker. Of course, you can continue to speak each other for a while, but the seminar is closed. So see you the next Friday.
Well, thanks for coming.
I will terminate the recording now.
Okay.